Morning. So in the last class, we discussed about the uh, trigonometric Fourier series coefficients and exponential Fourier series coefficients and relation between these two coefficients, C naught Cn related with A naught An and Bn. Similarly, A naught An and Bn related with C naught and Cn. Now we are going to discuss about the representation of a periodic signal, periodic function by the Fourier series over the entire interval, not limited interval, over the entire interval. Entire interval means from minus infinity to plus infinity. So already we discussed about the periodic function over the interval t naught to t naught plus t naught. So that is some limited interval. So outside this interval, Fourier series need not be equal. Beyond that interval means that is from minus infinity to plus infinity. It need not be equal. So Fourier series representation of the function over the interval t naught to t naught plus t naught is given by f of t equal to sigma n is minus infinity to infinity fn into e power jn omega naught t for the limited interval, that is t naught is less than t is less than t naught plus t. That is equation number 1. So here omega naught is 2 pi f naught or it is 2 pi by t. Okay, right. The two sides of the equation 1 need not be equal outside this interval. So consider RHS by phi of t. This RHS is phi of t. So f of t equal to phi of t for t naught is less than t is less than t naught plus t, where phi of t is sigma n equal minus infinity infinity fn into e power jn omega naught t for all values of t. Let it be considered as equation number 2. So it is simple to show that the function phi of t is periodic function with period t. Consider the function phi of t plus t. If phi of t is said to be periodic, it has to satisfy that condition phi of t equal to phi of t plus t, right? So now equation number 2 becomes phi of t plus t is equal to sigma n is minus infinity to infinity fn into e power gn omega naught t plus t, right? So it is equal to sigma n is minus infinity infinity fn into e power j n omega naught into t plus t is 2 pi by omega naught, or it is omega naught 2 pi by omega naught. So it can be written as e power j n omega naught t into e power j n omega naught 2 pi by omega naught gets cancelled. So it will become e power j 2 pi n, right? So since n is assumes only integral values, that is 0 plus or minus 1 plus or minus 2 etc., it is obvious that e power j 2 pi n is equal to unity or 1, and hence this equation becomes sigma n equal minus infinity infinity fn into e power j n omega naught t into 1. So that is fn into e power j n omega naught t. That is nothing but phi of t. So phi of t equal to phi of t plus t. Equation number 4. Okay, so it is periodic. It is also periodic beyond this interval. Beyond this interval also. So it is phi of t equal to phi of t plus t. So it is a periodic function, the given function. It is f of t is given. It is the periodic function. So f of t and its Fourier series over the entire interval minus infinity to infinity is shown like this. It is the Fourier series of this f of t. Similarly, phi of t is like this. It is a periodic over the interval minus infinity to infinity. Okay. Uh, Entire interval, that is f of t equal to f of t plus t. So f of t is sigma n is minus infinity infinity fn into e power j n omega naught t over the entire interval minus infinity to infinity, where omega naught is 2 pi by t. So fn equal to this fn equal to 1 by t into integral t naught to t naught plus t f of t into e power minus j n omega naught t dt. Okay, so that is about the representation of a periodic function by the Fourier series over the entire interval. So beyond the interval only, it is also periodic. So during the limited interval only, it is a periodic. Beyond that interval also, it is a periodic. Okay, that was proved as phi of t equal to phi of t plus t. Okay, phi of t is phi of t plus t was proved. Okay, right. So now coming to the properties of Fourier series. So here we have 8 important properties of Fourier series are there. So those are linearity property, time shifting property, frequency shifting property, time scaling property, time differentiation property, convolution property, multiplication property, and symmetry property. Okay, these are the very important properties of Fourier series. Coming to the linearity property, we know that a complex exponential Fourier series is expressed as x of t is equal to sigma n is minus infinity infinity cn into e power plus jn omega naught t. X of t is any continuous time periodic signal and cn is its Fourier quotient. For simplicity, let us denote these quotients as cxn so that the complex exponential Fourier series of continuous time Fourier series of x of t is Cxn, then the linearity property may be stated as if the CTFS, the continuous time Fourier series of x of t is Cxn and continuous time Fourier series of y of t is Cyn, then z of t is expressed as a into x of t plus b into y of t. The CT, continuous time Fourier series of a into x of t plus b into y of t is nothing but a into Cxn plus b into Cyn, that is Czn, right? So that is the linearity property. Second one is the time shifting property. Time shifting property. It states that if the continuous time Fourier series of x of t is Cxn, then continuous time Fourier series of x of t minus t naught is nothing but e power minus j n omega naught t naught into Cxn. Thus, the magnitude of the Fourier series quotients remain unchanged when a periodic signal is shifted in time, right? That is the time shifting property. Next one is frequency shifting property. How it is defined? If the continuous time Fourier series of x of t is Cxn, then e power k then omega naught t into x of t. The CTFS of e power jn omega naught t into x of t is Cx of n minus n naught. Here, shifting the frequency components by n naught is equivalent to x of t and e power jn omega naught. Okay. Next, time scaling property. Time scaling. So it states that x of t is a periodic signal at period t naught. Then x of t will be a periodic signal at period t naught by infinity, where alpha is a positive real number. Thus, the application of time scaling property, the period of a signal changes. So the time scaling property applies to each of the harmonic components of a signal x of t. Therefore, Fourier quotients for each of these harmonic components remain the same. So mathematically, this time scaling property is defined as if continuous time Fourier series of x of t is Cxn and continuous time Fourier series of x of at is Cxn also, Cxn only. So thus after the time scaling, Fourier series quotients are same. The spacing between the frequency components changes from 1 by t naught to a by t naught. Okay, next property is time differentiation property. Time differentiation property. If continuous time Fourier series of x of t is Cxn, then continuous time Fourier series of d by dx of different way because it is the differentiation property, that is d by dx of x of t is j into 2 pi n by t naught into Cn. Next property is time convolution property. The continuous time Fourier series of x of t is Cxn and continuous time Fourier series of y of t is Cyn, then z of t is defined as x of t convolved with y of t. The continuous time Fourier series of this x of t convolved with y of t will become t naught into Cxn into Cyn, that is nothing but Czn. Okay. Next property is multiplication property. The continuous time Fourier series of x of t is Cxn and continuous time Fourier series of y of t is Cyn. Then z of t is nothing but the multiplication of x of t and y of t. So the continuous time Fourier series of x of t into y of t is nothing but t naught into Cxn circularly convolved with Cyn, which is nothing but Czn. Next, symmetry property. It is defined as if x of t is real, then Cn star equal to C minus n. If x of t is imaginary, then Cn star equal to minus of C minus n. Okay. So these are the 8 important properties. By defining these properties, it is enough. Okay, so these are all the statements of all these properties. Next one is the complex Fourier spectrum. Complex Fourier spectrum. Complex Fourier spectrum. How to define this complex Fourier spectrum? Already Fourier spectrum is already discussed in the earlier topics. What is Fourier spectrum? It is combination of amplitude spectrum and phase spectrum over the period with the frequency components omega naught, 2 omega naught, 3 omega naught, up to n omega naught, etc. We have to draw the frequency spectrum, amplitude spectrum, as well as phase spectrum with the frequency components omega naught, 2 omega naught, 3 omega naught, 4 omega naught, up to n omega naught. It is in the form of discrete signal at so it is in the form of discrete signal, right? At various frequency components, it has some amplitude which is proportional to the vertical axis. So in the exponential Fourier series, the periodic function is expressed as a sum of exponential functions of frequency 0 plus or minus omega naught plus or minus 2 omega naught up to plus or minus n omega naught. So the significance of negative frequencies has already discussed here. Both signals e power j omega t and e power minus j omega t oscillates at frequency omega. So by adding these two, it gives a real function of time, that is e power j omega t plus e power minus j omega t is nothing but 2 cos omega t. As we already know that cos theta is e power j theta plus e power minus j theta by 2, or e power j theta plus e power minus j theta is equal to 2 cos theta. Here theta is replaced by omega t, that's why e power omega t. So it is e power j omega t plus e power minus j omega t is equal to 2 cos omega t, right? So for a periodic function of period t, the exponential Fourier series is given by f of t equal to f naught plus f1 into e power j omega naught t plus f2 into e power j 2 omega naught t plus dash 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 plus fn into e power j n omega naught t plus f minus 1 into e power minus j omega naught t plus f minus 2 into e power minus j 2 omega naught t plus dash 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 plus f minus n into e power minus j n omega naught t plus so on. Here the frequency is 0 omega naught minus omega naught 2 omega naught minus 2 omega naught up to n omega naught minus n omega naught, and the amplitude of these components are f naught, f1, f minus 1, f2, f minus 2, fn, f minus n, etc. If you take the periodic function for the rectified sine wave, so this is the sine wave, this is the half wave rectified or full wave rectified sine wave. It is the full wave rectified sine wave f of t versus t. Here the exponential Fourier series was found as f of t equal to 2a by pi, that is the amplitude, minus 2a by 3 pi into e power j 2 pi by t, and minus 2a by 15 pi into e power j 4 pi t, minus 2a by 35, like this, minus 2a by 3 pi into e power minus j 2 pi t, minus 2a by 15 pi into e power minus 4 pi t, minus 2a by 35 pi into e power minus j 6 pi t. So the spectrum exists at omega equal 0 plus or minus 2 pi plus or minus 4 pi plus or minus 6 pi and etc. And the corresponding magnitudes are 2a by pi minus 2a by 3 pi minus 2a by 15 pi minus 2a by 35 pi, so on. And the phase spectrum is not there. Why? Because the frequency spectrum, uh, here phase angle is 0, that's why there is no phase spectrum. So only we have the frequency spectrum. This is the frequency spectrum of a rectified sine wave. So the magnitude spectrum of every periodic function is symmetrical about the vertical axis passing through the origin. The quotient fn is given by fn equal to 1 by t into integral minus t by 2 to plus t by 2 f of t into e power minus jn omega naught t dt, and f minus n equal to 1 by t into integral minus t by 2 to plus t by 2 f of t into e power plus jn omega naught t dt, right? Here the quotients fn and f minus n are complex conjugates of each other. That is, fn is f minus n star, and magnitude of fn is magnitude of f minus n. If fn is real, then f minus is also real. Then the both are equal. Fn equal to f minus n. If fn is complex, that fn equal to mod fn into e power j theta n, then f minus n equal to mod fn into e power minus j theta n. The phase of fn is theta n, and the phase of f minus n is minus theta n. Here the phase spectrum is antisymmetrical, that is an odd function. Antisymmetrical means it is an odd function. and magnitude spectrum is symmetrical. It is an even function about the vertical axis passing through the origin. So phase spectrum is anti-symmetrical, means that it is odd function. Magnitude spectrum is symmetrical, that is an even function. These are uh, anti-symmetrical and symmetrical about the vertical axis passing through the origin. Okay, so far we discussed about the Fourier, Fourier series. So you have two different types of Fourier series, of the trigonometric form of Fourier series and exponential form of Fourier series. The relation, trigonometric and exponential, how these two are related, we discussed, and properties of Fourier series discussed it, and uh, and and representation of the periodic function over the entire interval is also periodic. Then complex Fourier series was also discussed. Then we are going to discuss about the Fourier transform. Okay, so we discussed about the periodic signals in our earlier topics. So the signal can be represented as linear combination of harmonically related complex exponentials. That is about the periodic signal. Coming to the non-periodic signal, the non-periodic signal can be viewed as a periodic signal with an infinite period. Here, there is a infinite period, but whereas coming to the periodic signal, here we have the finite period. Okay, here these can be expressed as continuous sum of external signals. Here we'll see the non-periodic signal. So the f of the figure 1, this is non-periodic signal. If we take figure 2, this is a periodic signal with a limited period. This is having the infinite period. Okay, so figure 1 shows non-periodic signal x of t, which is represented as continuous sum of exponent signals. Figure 2 represents the signal xp of t, which is obtained by repeating non-periodic signal x of t in figure 1 after every t naught seconds. So t naught is sufficiently large such that no overlap no overlap occurs between repeating non-periodic signals. Okay, non-periodic signals. Non-periodic signals. Okay, non-periodic signals. Non-periodic. Okay, so see See, from figure 1 and 2, let T naught tends to infinity of figure 2 is equal to figure 1. Let T naught tends to infinity xp of t is equal to x of t. The exponential form of the Fourier series for xp of t is nothing but xp of t equals sigma n equal minus infinity to infinity cn into e power jn omega naught t, where the cn is 1 by t naught into integral t naught to t naught plus t naught xp of t into e power minus j n omega naught dt. Let it be considered as equation number 1. Here the period t naught becomes larger and larger. Omega naught becomes smaller and smaller. Thus the frequency spectrum becomes denser. So it is illustrated. So it is shown like this. See the diagrams. This is fp of t or xp of t for various periodic signals, and this is the frequency spectrum of xp of t. So this is the given signal. Here the time period is very less, that is 1 second. So that frequency becomes 1 by 1, that is 1 hertz, and angular frequency is 2 pi radians. With 2 pi radians, we can draw the frequency spectrum like this. Okay, 0, 2 pi, 4 pi, 6 pi, 8 pi, like this. At 0, minus 2 pi, minus 4 pi, like this. So this is the second one. Here the time period is given as t naught equal to 0 to 2, that is 2 seconds. So f naught is 0.5 hertz and omega naught is pi radians only. So this is 0, pi, 2 pi, 3 pi, 4 pi, like that. Okay, so it will become denser when compared with this one. Okay, then the third diagram, which is the third diagram. Here the time period is larger, that is 4 seconds. So frequency is 1 by 4 and omega naught is pi by 2 radians only. So it will become 2 denser than this. Okay, similarly this is the non-periodic signal. So here t naught is infinity, so that omega naught is 0. So it is very very thin, very thick denser than the above one, earlier ones. So this is the spectrum. Frequency spectrum is a continuous function of omega. Okay. Next, coming to the concept explained in the above figure leads to the definition of Fourier transform. Definition of Fourier transform as T naught omega naught infinitesimal sum. Omega as T naught omega naught is infinitesimal sum and can be denoted as delta omega. So omega naught equal delta omega. Equation one is readjusted as n equal 1 by T naught to integral T naught to T naught plus T naught xp of T into e power minus Jn. Omega naught is replaced by delta omega into T, or Cn into T naught is equal to integral T naught to T naught plus T naught xp of T into e power minus Jn delta omega T dt. That is equation number 2. So here it is nothing but x of n delta omega, or Cn equal to x of n delta omega by T naught. That is equation number 3. Okay, substituting these equations 3 in equation number 1 and letting omega not equal to delta omega, then xp of t is equal to sigma n is minus infinity x of n delta omega by t naught into e power plus jn delta omega into t, or it is equal to sigma n is minus infinity x of n delta omega by 2 pi by delta omega t naught is replaced by 2 pi by delta omega into e power plus jn delta omega t, or it is nothing but x of n delta omega by 2 pi into delta omega into e power j delta omega, referring to figures 1 and 2. So as t naught tends to infinity, xp of t and x of t are represented as x of t equal to let t naught tends to infinity, xp of t, or x of t equal to let omega delta omega tends to infinity 1 by 2 point sigma n equal minus infinity x of n delta omega and e power jn delta omega t into delta of omega, or x of t equal 1 by 2 point sigma n is minus infinity x of omega into e power j omega t d omega. So referring to equations 2 and 3, we get x of n delta omega equal to limit t naught tends to infinity integral xp of t into e power minus j in delta omega t into dt, or x of n delta omega is equal to integral x of t into e power minus j n delta omega t into dt, or it is equal to integral x of t into e power minus j omega t dt, or we can write this as x of t equal to 1 by 2 pi sigma n equal to 0 minus infinity x of omega into e power plus j omega to d omega, where x of omega is integral minus infinity x of t into e power minus j omega t dt. This is equation number 5, and this is equation number 4. This is here equation number 4 represents non-periodic signal. Okay, x of t in terms of continuous sum of exponents with frequencies between minus infinity to infinity. Equation 5 gives amplitude of exponents at different values of omega, that is it represents continuous spectrum. Okay, this is continuous spectrum. This is the uh, non-periodic x of t in terms of continuous sum of exponents with frequencies between minus infinity to infinity. So 4 and 5 equations are referred as Fourier transform pair. Pair. Okay. So Fourier transform of x of t is x of omega. Then inverse Fourier transform of x of omega is x of t. Okay. X of t is Fourier transform of x of t is x of omega, and inverse Fourier transform of x of omega is x of t. Right. These two are called Fourier transform pair. Okay, then coming to the Dirichlet conditions. Here in Fourier series also we discussed about the Dirichlet conditions. We have three Dirichlet conditions are there. Here also we have three Dirichlet conditions are there. First condition is x of t is absolutely integrable. That is integral minus infinity to infinity x of t into mod dt must be less than infinity. Our summation with this Fourier transform. That's why here we will take the summation n equal to r n equal to minus infinity x of n into mod x of n into period must be less than infinity. It is some finite value. Next, x of t have a finite number of maxima and minima with any finite interval. Third condition is x of t have finite number of discontinuities within any finite interval. Furthermore, each of these discontinuities must be finite. These three are conditions are same as that of the Dirichlet conditions of the Fourier series. Now we will do some problems on Fourier transforms. Find the continuous spectrum for the signal x of t is equal to e power minus at into u of t, where a is greater than 0. U of t is nothing but defined as it is u of t equal to 1 and t is greater than or equal to 0. U of t is 0 for t is less than 0. Okay. So here we are taking the limits from 0 to infinity is enough. Okay. So x of omega equal to Fourier transform of x of t, that is integral minus infinity infinity x of t into e power minus j omega t dt. But here u of t is 1 for t is greater than or equal to 0. That's why. So here we will take integral 0 to infinity e power minus at into u of t is 1 e power minus j omega t dt, taking minus as common a plus j omega into t with limits 0 to infinity. So by simply substituting this, that is minus 1 by a plus j omega into e power minus of a plus j omega into infinity minus e power minus of a power j omega into 0. So this will become e power minus infinity. E power minus infinity is 1 by e power infinity, or it is 1 by infinity, that is 0. So this will become 0 and this is e power 0, that is 1. So minus and minus plus, so x of omega will become 1 by a plus j omega for a is greater than 0. Now we have to calculate the magnitude and the phase spectrum, so that we can get the, we can draw the spectrum, continuous spectrum for the signal. So how to find out the magnitude spectrum? Magnitude mod x of j omega, that is 1 by square root of a square plus omega square. Similarly, phase angle theta of omega equal to minus tan inverse imaginary term by real term omega by a. Okay. So now we can draw the magnitude and phase spectrum for this given problem. So by taking the values of omega, magnitude, and phase angle. So here we are taking from minus infinity infinity some values. Okay, minus infinity minus a 0 plus a plus infinity. And substituting these values in the above expressions, we will get different values for magnitude spectrum and phase spectrum. So after that, we will draw the plot magnitude spectrum and phase spectrum. Okay, that is about the that problem, e power minus 8 into u of t. Similarly, in the same manner, we will do some other problems also. Find the continuous spectrum of non-periodic signal x of t equal to e power minus a into mod t with a is greater than 0. E power minus a into mod t with a is greater than 0. You can write this as mod t is plus or minus t, so that it will become e power minus a into minus t into u of minus t plus e power minus a into plus t into u of t, right? Okay. So e power minus into where a is greater than it is given. So this is the diagram here. Okay. So it is a Fourier transform of x of t is integral minus infinity infinity x of t into e power minus j omega t dt. So integral minus infinity infinity e power minus in a into minus a t u power u of minus t plus e power minus 8 into u of t into e power minus j omega t dt, right? So integral minus infinity 0. This is u of minus t is value is 1. So e power minus minus t into this is 1 into e power minus j omega t dt plus integral 0 to infinity e power minus 8 into u of t into e power, this is also, this value is also 1. So it will become integral minus infinity to 0 e power 8 into e power minus j omega t dt plus integral 0 to infinity e power minus 8 into e power minus j omega t dt, or it is e power a minus j omega into t dt plus integral 0 to infinity e power minus of a plus j omega into t dt. So it is e power a minus j omega t by a minus j omega with limits 0 minus infinity, and it is e power minus of a plus j omega by minus of a plus j omega into with limits infinity 0, right? By simply substituting and simplifying this, we'll get x of omega value is 1 by a minus j omega plus 1 by a plus j omega, or it is 2a by a square plus omega square. A minus b into a plus b, that is a square plus a square minus b square. So a square is nothing but minus 1, so that it will become a square plus omega square. So it is 2a by a square plus omega square. Now we will draw the magnitude and phase spectrums. So how to represent magnitude expression, that is mod of x of a j omega, x of omega, that is 2a by square root of a square plus omega square. Okay, a square plus omega square, and here x of omega is real. There is no imaginary term, so there is no phase spectrum exists. So that magnitude spectrum is this one. Next problem. Find the continuous spectrum of non-periodic gate function shown. So this is the non-periodic gate function with limits -1 to 1. So here phi of t value is 1 from -1 to 1 and it's 0 elsewhere. Okay. So it is integral -1 to 1 pi of t in t power j omega t dt. So it is -1 to 0 and 0 to 1. Both are same. So -1 to 1 pi of t in t power minus j omega t dt. So let us take pi of t value is 1. So it is -1 to 1, 1 in t power minus j omega t dt. So -1 by j omega in t power minus j omega minus e power minus j omega limits 1 in -1. So it will become 2 by omega into e power j omega minus e power minus j omega by 2j. So this is nothing e power, it is in the form of e power j theta minus e power minus j theta by 2j, that is sin theta. So that it will become sin omega. So it is 2 by omega into sin omega. So magnitude m equals 2 by omega and sin omega. There is no imaginary term here. So there is no phase spectrum. Only we have the magnitude spectrum. So by taking the different values of omega here and simply substituting these omega values in this expression, we will get the magnitude spectrum values are like this. For these values, we can draw the spectrum. Okay, that is about the phi of t equal to 1 function. Okay, so with this, these are the Fourier transform problems. In the next class, we will do some other problems. With this, I am concluding the today's class. Okay, thank you.